Did you know who and how invented quantities, such as kg or meter, time, or speed of light? What is the accuracy of physical quantities, and how can this accuracy be depicted? How does the science of physics study nature? First, scientists observed. Then, to explain what they observed, they felt that it was necessary to somehow interfere with physical phenomena. What is the name of the study of physical phenomena in artificially created conditions? It is called, as we all know, experiment. That is, physicists moved from observation to experiment. Experiments made it possible to put forward some kind of hypothesis about why the phenomenon occurs one way or another, to confirm this hypothesis or to refute it. People set up new experiments and then, based on these experiments, physicists built a theory, that is, some kind of then a mathematical model, a mathematical description, therefore, to be able to study the world around us. We need to use mathematics, and mathematicians operate with some quantities, with numbers. And now we will talk about how physical quantities appeared in physics and what it means, measurement. Imagine the following situation. You are discussing, for example, the weather and you are talking about cold today. Today is cool in September morning, unlike last day, but how cold is it? When you say cold, you get a feeling that is familiar to you based on life experience, but imagine this situation. 2 planes landed at the airport this September. One flew in from Greenland and the second flew in from Ecuador. Greenland is far to the north. The name Ecuador itself says that it is located on the equator of the Earth, and now passengers get off the plane that flew in from Greenland and say, "Wow, what heat!" And the inhabitants of Ecuador go out and they are shivering from the cold because they are cold. Indeed, the thermal conditions for the inhabitants of Greenland and the inhabitants of Ecuador are absolutely the same. They left in the same airport, which means that it is cold for some and hot for others. That is, the feeling depends on who feels. In other words, the concepts of heat and cold remain subjective. That is, depending on the observer, on the one who experiences this sensation. But how can it be done so that all people receive the same result, the same information about the state of the atmosphere? You need to enter a value, and what does it mean to enter a value? What is the difference between a physical quantity and a mere physical concept? The physical concept depends on the properties of the observer, on his habits, on his way of life, and the physical quantity has an exact value. So it turns out that the physical quantity is a physical concept that is expressed using a number. But how to express a physical concept using a number? We need to measure, then we can formulate what a physical quantity is. A physical quantity is a physical concept expressed by a number in the process of measurement. Physicists ask themselves the question, what should be taken as a unit so that all people in the world understand how to measure this quantity, and came up with the word standard. For example, we need some specific length segment. We are talking about a measurement of length, which we will conditionally consider a unit, and for example, they took the length of the feet of the King of England and took it as a unit. The king is still one for the whole country and called this unit feet. When the king dies, and the unit of feet will need to be changed. People agreed on what it is equal to. But this is still not a very accurate definition. You need to make a device that would allow you to store a unit of physical values and reproduce it. And we will call this device the word that already mentioned, standard. The most common physical quantities are length, time, and mass. For example, how is the length standard arranged? The first standard of length was called Demeter. It was created in 1793 during the French Revolution, when the French in general wanted to turn the world around for the better and came up with this method. They very carefully measured the length of the meridian passing through Paris and agreed that 1 meter would be equal 140 million length of the Parisian meridian. They took such a rod and struck 2 corners and said this is exactly meter. This standard is kept to this day near Paris in a town called Sevres. But what is the disadvantage of this standard? Is it accurate or not? It is accurate, but it has a very important drawback. It can be lost, and nothing lasts forever. Are there any objects in the universe that, firstly, are not afraid to lose, and secondly, are they all the same? Yes, it's in atoms. For example, all hydrogen atoms are the same, an electron and a proton. All protons in the world are the same, and all electrons in the world are the same. So, if we want to make a standard that is not scary to lose, which can always be reproduced, we need to be based on the properties of atoms, and one of the properties of atoms is to glow under certain conditions, and light is a wave, and a wave is characterized by length, and so it turns out that modern standards for lengths, although they are no longer modern, rely on the wavelength of radiation that is emitted by atoms under certain conditions. For example, krypton atoms 86, and based on krypton atoms, we can formulate that 1 meter length or equals 1,650,760 wavelengths of radiation. In the same way, we also need a time standard, but this is where difficulties arise because time is always flowing. The standard of time at one time was the rotation of the globe, but then it turned out that the time of one revolution of the globe changes, the Earth rotates more and more slowly, because it is slowed down, for example, by the Moon. And when they found out that the rotation of the Earth was slowing down, they built another standard, more accurate, and this other standard was again based on processes in cesium atoms. As a standard of time, electromagnetic oscillations that occur in cesium atoms are used. At first, a very complex device was used as a target standard. The fact is that now electronics is developing so rapidly that it is possible to make a standard with the same properties, but placed in microchip, and such microchips are now flying on GPS satellites. They set the time for a very accurate determination of the position of bodies on the surface of the Earth. And if you want to know the exact time, it is best to turn on the GPS navigator, and it will give you the most accurate time. But there is another problem, the mass standard, and this problem still has not yet been resolved. The fact is that until now, the standard stored in Severs, France, and the mass of this standard is taken as 1 kilogram. This platinum-iridium alloy cylinder is kept under caps to keep it dust-free. This is the most unfortunate standard because it can be lost, but what would be a more successful standard that would not be scary to lose? The candidate for the manufacture of a mass standard is silicon, for example. These are not official mass standards, but the future is possible behind them, such as a silicon ball, and the idea of using silicon is that the number of atoms in it is already counted. This standard is not real, it is unofficial. Behind the standards working on that principle is the future. If we compare the accuracy of the length standard with the accuracy of the time standard, then the standard of time will win, because the standard of time is more accurate than the length standard. That's why people are better at measuring time precision than length. The difficulty is that when you make a standard, you can say that this is a meter, but if some changes occur in the atoms, or suddenly, for example, the force of gravity changes, then the standard will work a little differently. So that's why this standard should not be subject to any changes. So it turns out, for example, that the same force of gravity, and this has been experimentally proven, affects the behavior of atoms. There is such the Mossbauer effect, for which the Nobel Prize was received. They use the fact that the rate of processes at the surface of the Earth, where gravity is a little bit more and at a height of a few tens of meters above the ground, is slightly different. This is called gravitational redshift. So, the most accurate standard is still the time standard, and the most accurate speed standard is the speed of light. But it is only necessary to add that we are talking about speed of light in a vacuum. The speed of light in a vacuum was measured many times, and it was found out and experimentally confirmed that the speed of light in a vacuum is not only always constant, it also does not depend on in which system the observer is located, and the speed of light in any frame of reference equals to 299,792,458 meters per second exactly. If the video was useful for you, subscribe and like the channel.